Great evening, great evening. For today, we are going to focus on chemical equilibrium. Chemical equilibrium. So now, in this topic, there are 3 points that we are going to focus at. The first one is chemical equilibrium and factors affecting equilibrium. It's what is a chemical equilibrium and the factors affecting equilibrium. It is the first point. Now the second pointer will be equilibrium constant, which is the Kc. Equilibrium constant, which is the Kc. The third point is application of equilibrium principle. Application of equilibrium principle. So these are the 3 factors that we are going to focus on for today. But now, today, for this lesson, let us start first with what? The chemical equilibrium and factors that are affecting equilibrium. Chemical equilibrium and the factors that are affecting equilibrium. Now, before we get to that, we first have to try at least to explain. We first have to try and explain an open system and a closed system. So now, when we speak of an open system, it is a system that is continually or continuously interacting with its environment. Let me just say open system. An open system, let us make an example. An open system is something like this. When water is being poured into a beaker and it is not closed, it means when this water evaporates, this water will go where? Will go into the environment. It will evaporate and leave the beaker empty. That is an open system. But a closed system, when we speak of a closed system, now this one, it is whereby we have a container that is being sealed. By the word sealed, it means there is nothing that is going to leave this container or our beaker. It means even if this water in this beaker is being boiled, the water will boil and will come back again, meaning the water will evaporate and condense again, meaning here the 2 processes will take place, which is condensation and evaporation. And remember that condensation, it is that stage whereby a gas turns back into liquid. So now in a closed system, this is whereby there is no water particle that will leave our container. So we will explain more about the closed system as we go on. But now, just to highlight, the factors that are affecting equilibrium are, number 1, it will be pressure, mainly for gases. It will be the concentration and the temperature. Those are the 3 factors that are affecting equilibrium. But now I want us to explain a little bit more of what of the closed system. So now some of the reactions they go straight into completion. So now how do we tell if a reaction goes straight into completion? Let's take an example with this reaction. This reaction goes straight into completion. How do we see that? We see it by this arrow. This arrow shows us that this reaction goes directly into the completion. But if we have something like this, A plus B, then we have two arrows like this that forms C plus D. What does this mean? It means A and B can be broken into C and D, and also C and D can be broken into A and B. This means that it is a reversible reaction. This reaction can form this reaction can also form this. It is what we call a reversible reaction. This one, the second one, it is what we call a reversible reaction. It is what we call a reversible reaction. It is what we call a reversible reaction. We are going to try and explain this reversible reaction using the diagram so that we can at least have a full understanding of how it actually happens. Now, let's start with beaker A. Remember that the reversible reaction happens in a closed system. Reversible reaction may happen in a closed system. Let me just now. In this beaker, it is our first beaker. Now, the amount or the rate of evaporation will not be the same as the rate of condensation. Now, this simply means here it is whereby our water has just been poured into a beaker. So in this case, we have not yet reached equilibrium because the rate of evaporation, it is not the same, or it is not equal to the rate of condensation. Now let's move forward, and you must also remember that this reversible reaction, it does not end. It keeps on going up until we reach a constant temperature. So now our second diagram is going to be B. This is whereby now the rate of reaction, the rate of evaporation is equals to the rate of condensation. But now here it is at a lower temperature. We see by the water droplets that are now condensing and forming into a liquid again. Now we move forward to our last diagram, which will be diagram A. Here we can clearly see that the amount or the rate of condensation and the rate of evaporation, they are equal. Now this is whereby we call it now an equilibrium is being reached at a higher temperature. So now let me try and explain them now, because now I have already drawn them. Now, if our beaker has a lid, meaning it is being closed in a way that there's nothing that will leave the beaker, the water will evaporate and condenses again. The water will evaporate and condense, evaporate and condense. Now, evaporation and condensation will occur at the same time. This is whereby our arrows here, they are now equal in length. This is whereby our evaporation rate and our condensation rate will happen at the same time. And eventually, water evaporates and condenses at the same rate. And in this way, this is whereby we are going to reach our dynamic equilibrium. So when we speak of dynamic equilibrium, we speak of equal amounts of what rate, meaning the rate of evaporation is equal to the rate of condensation. That is where our dynamic equilibrium occurs. Now, you must remember that the reaction does not stop. It evaporates and condenses at constant rates. And the overall effect appears to be no change, meaning there won't be no change because the rate of what? The rate of evaporation will be equal to the rate of what? Of condensation. We can even make a chemical formula and say, let's just use H2O, which was a liquid at first, and then now it is experiencing dynamic equilibrium, which means now it is going to be H2O, but now as a gas. As a gas, meaning this H2O as a gas can turn back into H2O in a form of liquid, and this H2O in a form of liquid, it can turn into H2O in a form of a gas. So now the last part that I want to highlight is there are requirements that are needed in order for us to reach a chemical equilibrium. For us to reach chemical equilibrium, we must have, it is very important, a closed system. We must have a closed system for us to reach a chemical equilibrium. So now, the last part that I want to explain here, it is just the Le-Chatelain's principle. We have to know this law or this principle. You have to know it by heart because they might ask this question in examination or in a test. The Le-Chatelain's principle that states that when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. So this principle, it is very important. You have to remember it. It might be about 2 or 3 marks. So it is very important to know the principles and the laws. So in our next lesson, we will focus on what? We will focus on the application of the Le-Chatelain's principle. Thank you.